Hello and welcome back to the study of curves. In the first video, we went over the details of how a curve is defined, its arc length, and then the most important part, the arc length parameterization. Today, we're going to talk about the derivatives of curves and the length formula. The main question is, when do we have the following length formula hold? This is a theorem, not the definition of the length, as you may have seen in an undergraduate course, where if your curve is C1, this is the right-hand side is given as the very definition. But remember that we defined length in a different, more metric way, which makes sense for only continuous maps. And now we're asking, when is this formula true? There are several ingredients for that. First of all, gamma has to be differentiable, so we can talk about gamma prime, at least almost everywhere, so that we can integrate it. But it turns out that this is not sufficient. We could have gamma differentiable almost everywhere, but the formula could still fail. And the reason goes all the way back to even real valued functions. The fundamental theorem of calculus can fail for reasonably nice functions. The most famous one is Cantor-Vitali function, built based on the Cantor set. There are explicit ways of constructing it. The Wikipedia article has it already. So this is a continuous and increasing function defined on the unit interval. And without loss of generality, it goes from 0 value to the 1 at the end of the intervals. It is differentiable almost everywhere, and the derivative is 0 almost everywhere. So from this, we can easily see that u1 minus u0, which is equal to 1, is not equal to 0, which is the integral of the derivative. And that is exactly what the opposite of the fundamental theorem of calculus. So for such a function, although it's differentiable and we can integrate its derivative, the formula, the equality fails. If we consider u as a curve with rd being r1, this is already an example of the length formula failing for a curve. But if you want it more interesting, you can make it a planar curve. So the graph of the Cantor-Vitali function, it's difficult to draw, but I will try. So it's something like this. It increases, but you never see when exactly. And this t gamma tut is traveling along the graph of this curve. And if you write both sides of the length formula from previous slide, they will not match. Indeed, the integral of gamma prime will be equal to 1. And obviously, the length of this curve is not 1 because you're joining it to 1, 1. And remember that the length of the curve is bigger than the distance of the endpoints of a curve. So here, bigger than root 2. Therefore, these cannot be equal because root 2 is already more than 1. Okay, so we have to deal with the question of when the fundamental theorem of calculus actually holds. And that was a very important question around 1900s. And Lebesgue came up with some condition, but Vitali came up with a more elegant way of stating those conditions and a definition. What he did was he defined the class of so-called absolutely continuous functions, which I will denote with AC. And he proved that AC is basically the largest class where FTC holds. So it gives a full answer to the question. And of course, this includes the claim that AC functions are in fact differentiable, so that you can begin actually to write the formula down. So what is an absolutely continuous function? This is a very strong form of continuity, even stronger than uniform continuity. Given any epsilon and any delta, you for any finite collection of non-overlapping intervals, if their sum of their length is less than delta, then the difference of the endpoints added up is less than epsilon. So the simple uniform continuity will be if you take just one interval. But here it's saying that, okay, you take multiple intervals. If their length add up to no more than delta, then yeah, this quantity does not add up to more than epsilon. The terminology, interestingly, agrees with the terminology from the theory of LP functions. So absolute continuity for integrals is saying that if you have integral of f over some set finite, then for every epsilon positive, there exists delta positive, so that for every measurable subset of E, if measure of f is less than delta, then integral of f, let's say f is non-negative, over f is less than epsilon. And you can see the analogy. So here you can take f to be this union of intervals as your measurable set f. So this is saying that if measure of f is less than delta, then integral of f is less than epsilon. If f is a bounded function, this is actually immediate for integrals. But the point is, even if f has blow-ups, goes to infinity, we could very easily have that, although this is finite. Even if you concentrate f around the set where the function f blows up, you still get this. So that is a good coincidence that the terminology agrees, and also makes more sense looking at it this way than this summation formula. So the point is that absolutely continuous functions are differentiable. Their derivative is integrable. If you are defined on all of R or defined on an open interval, this will be locally integrable. Here we have a compact interval actually, so this is just integrable. And then if TC holds, so integral of f prime from any, not let's say A, any C to D is f of D minus f of C. So if you have this, then you can go through this, and then from this you obtain that. So the reverse is true. So again, more justification for the terminology. And these three are basically equivalent to the other one, to being AC. So there needs to be a precise theorem stated, but I don't, because actually I will have separate videos just focusing on the theory of BV, which is coming next, and AC functions. There I will go in more details about these stuff, but what is written here is that these three conditions are basically equivalent to the last one. So your AC function, if and only if the three above holds, and if the three above holds, then you are an AC. And this thing that I talked about here about integrals can be used to go in some of these directions. Okay, so this is the definition of absolutely continuous functions, definition due to Vitali, and these bullet points are the significance of this class of functions. And notice that because this is an if and only if condition, the definition of Vitali is very natural and unavoidable. So you cannot unlike this definition. It is just there. It's an if and only if condition. And Lipschitz functions are absolutely continuous. It easily follows from the definition. You can epsilon and delta are related by this Lipschitz constant. Okay, another class of functions that are important are the class of so-called bounded variation functions, or BV functions for short. So again, for a real valued function u, we define the variation of u through this summation over all finite partitions of the domain. This, of course, is familiar because this is exactly the same definition we used for length of gamma. So here, if you look at U as a curve, although an uninteresting one that goes into R1, it's really not curvy, but technically it's a curve. So this is exactly the same definition. So bounded variation will be bounded length. Lipschitz functions, as we mentioned, are absolutely continuous, but absolutely continuous functions themselves are a subclass of bounded variation functions. Monotone functions are BV, and indeed there is an inverse kind of to this, that BV is difference of monotone functions. Therefore, because Vitali counter function was increasing, it is BV, but it is not AC because fundamental theorem of calculus fails for it. And here comes the most significant theorem about BV, that they are differentiable almost everywhere. Okay, so we talked about fundamental theorem of calculus, that it holds for AC, and also we talked about BV, and we saw that fundamental theorem of calculus does not necessarily hold for BV. What does all of this have to do with curves? The connection is through this lemma. This is not at all difficult to prove. It's just definitions. And the fact that the length of a vector A1, AD in RD is less than or equal to A1 plus A2 plus AD. This is saying that the Euclidean norm is less than the L1 norm, if you're familiar with that. So if you follow the definition of length, which was summation of distance of gamma ti minus gamma ti minus 1, and then apply this inequality here from that and definition of variation of real valued functions, you get to this inequality, that the variation of every component function is less than the length, and the summation of variation of the length, the summation of variations of components is bigger than the length. Therefore, if a curve is rectifiable, this is finite, that means, if and only if each one of these guys is finite. That's an immediate consequence. So what we get then is that if you have a rectifiable curve, then gamma prime exists almost everywhere. So that is the first ingredient we needed for the length formula, the derivative. If it's rectifiable, each component is of bounded variation, and we saw that BV functions are differentiable, so each gamma I is differentiable. Therefore, gamma prime exists almost everywhere. So we can actually formulate the length formula, but we saw that for BV, the length formula can fail. You do have the derivative, but you integrate it and you do not recover your function. What we can do is we go to the right class of functions where fundamental theorem of calculus did hold, and that was absolutely continuous functions. Here we talk about curves, but there's an easy way to define absolutely continuous curves. So although I put it as an exercise here, but let me, for completeness, say that, for example, we can say a curve is absolutely continuous if and only if each individual component is an absolutely continuous function. Or you can just revise the definition of absolute continuity, and instead of just absolute value of real numbers, use the norm of vectors. Anyway, the question of when the length formula holds was settled by Tonelli based on contributions from Vitali. Any rectifiable curve, a curve with finite length, is differentiable almost everywhere. We just saw that because it's BV. And the length is always bigger than or equal to the integral of the speed. This is always true. As soon as you are rectifiable, this is true. Interestingly, even if you're not rectifiable, this is true, because then this is infinity, and whatever happens on the other side will be there, will be smaller. But the point is, if you're not rectifiable, you don't know if it is differentiable. So technically, you cannot remove rectifiability condition here. Anyway, and the equality holds if and only if you are absolutely continuous. And that is brilliant. It completely answers this question. You have this inequality and it's equal if and only if you are an absolutely continuous curve. So absolutely continuous curves are the right class of curves for which the length formula holds. One important subclass yet is, of course, that of Lipschitz curves. Curves that are parameterized by arc length are Lipschitz. We had seen that, are in fact one Lipschitz. So the length formula holds for these. Also, we can restate the previous theorem using the arc length function. Recall that arc length function was a real valued function, not a curve, defined this way. The first theorem, lemma, whatever, is that gamma t is absolutely continuous if and only if this st is absolutely continuous. S prime of t exists almost everywhere because it's a monotone function. So even if you're not absolutely continuous, the derivative still exists. That's the point. Because it's monotone function, it has only countably many bad values, bad points. But I don't want to claim that it's differentiable except for countably many points. But anyway, this does exist. In the videos on the theory of BV and AC, I will definitely cover this. And the second claim, very important here, is that S prime, in fact, equals gamma prime norm. This is very important. This is a real valued function and its derivative. This is a vector, but we take norm to get a real number. It turns out that these are equal almost everywhere. So if we replace this equal with this in the Vitali's theorem, we end up with this, that if you are a rectifiable curve, then S prime exists almost everywhere. This exists almost everywhere. This is equality and this is inequality. And when does inequality become an equality? If and only if you are absolutely continuous. And because of this point here, either check S or check gamma, whichever we have information about. So if one of them is absolutely continuous, so is the other one, and the length formula holds. And that is the end of the story of length formula, but I want to end with the cute fact about the length of the graph of Vitali Cantor function. So remember, I had this not so accurate picture of how Cantor-Vitali function works. So my axes are differently scaled. So this is 1, 1. So we know this graph goes up there. We know that the length of this is at least √2. And we know that the length formula fails. Just because, yeah, the derivative of gamma prime exists. To be thorough, this is the curve we are talking about. So ut is the Cantor-Vitali function. And this is the curve that I'm talking about, the graph of it in the plane. And the integral of, if I call this gamma t as my curve, the integral of gamma prime norm is 1. So it is not equal definitely to the length of gamma. But what is the length of gamma? The answer is 2, and this is based on some stuff about PV functions from Leone's book that was in my references. And that is interesting because 2 is equal to this plus that. So the length of this curve you see here, the graph, is equal to the sum of the blue segments. But that is quite strange because this says that the Cantor-Vitali function has never moved diagonally. Because if you're in this point and in this point, if you move diagonally, it's faster than going this and then up, right? We've learned, or we know from, I don't know, human perception that anytime you go diagonally, you save some length. The worst is to go just horizontal and vertical. But here it's saying that in no movement along this curve, between no 2 points, have you made any diagonal movement effectively. You've never saved any length by going diagonally. And you have traveled just as much as if you had traveled, again, just horizontally until here and then vertically up. And that's just part of the craziness of this function. Hope you have enjoyed all of this material. Please put your questions in the comments for me. I would love to see them and answer them. I will continue next study of curves in general metric spaces, and that is just amazing because we will even talk about the length formula in that generality. Hope to see you in that video. Thanks a lot and take care.